Hello, everyone. In this video, I'm going to talk about the instruction encoding in assembly language. As we have seen, there are several different ways that instructions are written depending upon what types of information they need. For example, we have arithmetic instructions. Each arithmetic instruction needs 3 registers, or we have transfer instructions, load board and store what they need to register, and some offset, or we have branch or jump instructions. So they need to give them a label. Also for the branch we have to compare to register their content and then jump to the another address of the memory. So we have different type of the instruction and each one has different type of parameters. In MIPS architecture, there are 3 instruction formats and all of them has 32 bits in length. The first 6 piece of code appears at the beginning of each instruction. These 3 different formats are arithmetic, instruction, format, or R type, transfer, branch, immediate format type, and jump in instruction format or J type in instructions. As you can see, the first 6 feet of all of the R type, I type, or DJ type instructions is reserved for opcode or operational code for the R type. We should mention the 3 different registers that should be used by the instruction. So we have 3 parts: register source 1, register source 2, and destination or result register. Also there are some parts for shift amount for the shift left and shift right instructions, and we have 6 bits for function for the I type, for example, for the load word, store word. We need to register and some others. Also, this type can be used for the instruction with immediate auto racing mode like add immediate. We have to register and some immediate value that we want to add or subtract from some of the register. And the result should be stored in the target register. And for the jump instruction, we have 6 bit for opcode and the remaining can be used for determining the address of the target label. We will discuss this reformat of instructions in the remaining of this lecture. Our format. This instruction format will be used for all new instructions add, subtract, and or as. You remember in all of these arithmetic instructions, we use 2 registers for source and 1 register for destination. Since we have 32 registers in MIPS assembly language, in order to determine one of them, we need 5 bits. So this 5 feet determine the first source register. Second source register should be determined by this 5 feet, and the destination or result register determined by this 5 bits. The shift amount only will be used in the shift instructions, and the function code determine the instructions. In all format, in all of the OR format, the opcode is 0, and this part is different from one instruction to another one. Add, subtract, and or each one has a different function. This 6 bits has different code, but the opcode is 0 for all of them. So function code specifies which operation should be performed by this instruction. Let me give you an example. Consider the add in instruction. Add $, at $17, $18. As you remember, each one has a convenient name, or we can use the number to refer to the register. Here we use the numerical format. The opcode will be 0 because this is the arithmetical instruction. This is the first source register. This is the first source register. So 17 should be converted into the binary and placed here. As you can see, 10,001 is the binary notation for 17, and next 5 will be built by binary version of the second source register 18. And you can see here, and the third one is filled by binary notation of destination register or result register. It is 8, write it in 5 bits, and it is here. The shift amount will be 0 because in this instruction we do not have any type of shift. So shift amount is 0. And finally, the 6-speed function code is 32. Each instruction has a unique function called AD is 32. You can find the function code for all of the instruction in instruction manual. So the control unit, by checking this 0, find out that this instruction has AR type, and then by this 32, the control unit, find out that this is the instruction and then send the necessary signals to the oil route and the data flow, provide the sources and prepare the destination, location, and the control unit. Then necessary command to the OILU to perform addition. The format works well for all OILU type instructions, but we cannot use this format for other type of instructions, such as transfer instruction or branching instructions, for example, in the load word. As you remember, we have to register and one offset. So if we want to use the same format for the offset part, we have only 5 bits, and by 5 bits you can only mention the offset plus minus 16 location, so it cannot be useful. So we use other format for branch and transfer instruction. This is the format. As you can see, again, the first 6-bit is used by opcode and then we have to register. That should be converting to 5 bits and put it here. This 16-bit can be used for mentioning the immediate data, or it can be used to specify the relative address of the target label. For example, consider this instruction add immediate $8, 9, 9, and 1. So the add immediate opcode is 8. We will put it here in 6-bit. The $8 and 9 will be mentioned here, and each one of them we use 5-bit. Finally, this one should be converted into 16-bit and placed here. Well, pay attention that this 16-bit concept has assigned value. So this is the positive one. But in the branch, in instruction, we will use this 16-bit as the branch destination by using PC relative address. Consider this example. Here we have a branch, not equal instruction. If these two register contents are not equal, then jump to the exit, and exit label is here. How we can specify this exit label address in the machine code? We need to specify the address of this location. As you remember, the address of each memory location is 32 bits, so we cannot use the absolute address value for mentioned in the instruction because the whole instruction is only 32 bits. We cannot mention a 32-bit address inside this instruction. Instead of using this absolute automatic mode, we use PC relative or anything. As you remember, when the CPU execute this instruction, the program counter the specify to this location to next instruction. And we know that each instruction size is 4 byte. So if we have this address inside the program container, then this location will be program counter plus 4. And this location or my target address is program counter plus 8. So I will use this 8 as the program counter relative address offset and put it inside the machine code. So here branch not equal, opcode is 5 is 8 and 21 will be mentioned here. And then the program counter relative offset for the exit label 8. So this number will be add to the program counter value. And by this way, the process will find out the target address or branch to the exit label. This encoding method is not optimal. As you remember, each instruction takes 30 to beat and every utterance must be a multiple of 4. Therefore, we can use this simple formula in order to find the branch address of an instruction. So, the 16-bit immediate value will be multiplied by 4, and then this number will be add with the program counter. In the previous example, instead of putting 8, I can put 2 here and these 2 will be multiplied by 4 and then will be add with the current value of the program counter. And by this way, we compute the address of the target label. So by this way, the range of the target label can be multiplied by 4. So assume that the target is the label of plus b, it can be computed by program counter plus 4 times the immediate 16-bit value. If we consider the authors of the next instruction as the then this part will be b-ac. Relative byte address, but we put b-a divided by 4 in the immediate part. If the program counter value is this number, then by this 16-bit optimum version of the relative address, we can jump to a label in this range -2 over 17 byte up or plus 2 power, 17 down. So if we want to jump to somewhere far away from this range, then the assembler converts your code into 2 sections. If these 2 register are not equal, branch to label L1 and L1 is far away from this current location. The assembler converted into two-section branch, not equal to the L to the inverse of this one, and then by use another instruction jump L1 we jump to the L1. We will learn about the jump or J-type in instruction in the remaining part of this PowerPoint. So if the target is greater than £2.16 away, then the compiler invert the condition and insert an unconditional jump instead of it. Another example for I-format load worth $910 and $0.99 with the memory allocation that computed by adding these two value the content of register 9 and this offset and then put it inside. The $10 load board instruction opcode is 35 is 10 and this 9 will be mentioned as 2 first and second source registers and this offset will be converted into 16-bit and will be put here. So the I format can be used for transferring instruction, branch instruction, immediate instruction. The last in instruction format is J format. This format is used by jump instruction and jump and link instruction. This format uses absolute addressing. Actually, it's used pseudo-direct addressing because if you want to mention an absolute address, you have to use 32 bits and we cannot mention 32 bits here. We have 6 bits for the opcode and the remaining will be used to mention the pseudo-absolute address of the target. Again, we use word addressing, so the value that you put here will be multiplied by 4 and that number will be used as the target. And also in order to convert this 26 bits into real 32 bits address, the 4 upper bits of program content will be selected and concatenate to this target value. So in fact, when we multiply this 26-bit by 4, we have 28-bit because 20 will be added in the right side. And then the 4 bits come from upper bits of program counter. And by this way, we compute the target address. Let me show you an example. Yeah, the 26-bit address. Multiply by 4. So we have 20 in the right side and then the 4 upper bits of program counter concatenate to this 28 bits. By this way, we find the 32-bit address of the target. So this is the 26-speed immediate world address. We shifted 2 bits to the left and then we concatenate the leftmost 4 bits of the program counter to this 28-bit address.